Hi everyone, so this is Derek from Broadcom. So today we are going to talk about the quantum resistant Kubernetes. So how to secure the cloud native infrastructure for the post quantum era. So basically we are preparing the distributed systems for the quantum computing revolution. So that will fundamentally change how we approach the cryptographic security in cloud native environments. The quantum threat landscape. So today, the classical cryptography protects our systems, RSA and EPC. RSA remains secure against traditional computing attacks. But in this quantum era, the quantum computers emerge with sufficient powers to break the RSA and EPC using Shor's algorithm. So what next? So the post-quantum era, traditional encryption becomes obsolete. Organizations need quantum resistant alternatives. So, how are you going to do that? Let's see. So, first of all, let's analyze why Kubernetes is exposed. Kubernetes security is fundamentally built on public key infrastructure (PKI) and transport layer security (TLS). So, every critical communication path relies on classical cryptography that quantum computers will break. Example: the API server, which clone cluster state communication protected by TLS certificate vulnerable to quantum attacks. And the pod communication, which is again a service mesh. So the mutual TLS connections between microservices rely on RSA and ECC key exchanges. Then the Ingress client traffic. So the external traffic that enters through the TLS terminated load balancers using quantum vulnerable certificates. And the final is the ministry cluster, which contains the image folds and pushes authenticated through classical cryptographic signatures. So what's the impact on cloud native security? So when quantum computers break PKI, the end-to-end foundation of Kubernetes security collapses, the consequences extend far beyond simple data breaches. So what are those? So it's basically it is the compromised TLS, exposed secrets, fake identities, and vulnerable backups. So what is compromised TLS? Man in the middle attacks become trivial. All encrypted communication can be intercepted and decrypted in real time. And the exposed secrets. So what are those? It's the database passwords, API keys, and the service tokens stored in Kubernetes. Secrets become readable by the attackers. And the fake identity. Malicious bots can impersonate legitimate services. Service identity verification becomes impossible without, without quantum safe signatures. Then the vulnerable backup. Historical data and backup systems encrypted with classical algorithm face future decryption threats. So Kubernetes without secure PKI is like a bank without vault door. Trust becomes impossible to establish or maintain. So now entering the post quantum cryptography, PQC, the National Institute of Standards and Technology, the NIST, has completed its post quantum cryptography project, providing standard algorithms resistant to quantum attacks. So they are called the Kyber dilithium hybrid cryptography. So the key encapsulation mechanism for the secure key exchange based on the lattice cryptography problems that remain hard even for quantum computers. Then the digital signature algorithm providing authentication and non-repudiation in the post-quantum era. The transition strategy combining classical and post-quantum algorithms for backward compatibility and enhanced security. So this standardization provides a clear path forward, making transition from optimal to inevitable for on serious about long-term security. So let's now see the PQC in Kubernetes. The post-quantum cryptography must be integrated at every layer while Kubernetes relies on classical encryption and digital signature. So basically on the Ingress controller, service mesh, the etcd, the container registry. So in the Ingress controller, the TLS termination points where external traffic enters the cluster. So etcd is the encryption at rest and API communication for cluster state storage. And the service mesh, it is the mutual TLS connections between the microservices and file card proxies. container registries, image signing, and verification for supply chain security. And now let's see how the quantum safe Ingress works. So Ingress controller serves as the primary entry point for external traffic, making them the most critical component to secure in the quantum resistant transition. The client which initiate the support hybrid TLS handshake with both classical and post-quantum algorithms. Ingress, the key replaces RSA and ECC while maintaining backward compatibility. The pod which receives the quantum safe secured encrypted traffic from Ingress controller. Implementation support is already emerging in OpenSSL PQ branches, NY proxy, and Nginx, starting with immediate protection for the most exposed attack surface. So, how hardening the service mesh can happen? Service meshes like Istio and Linked rely heavily on mutual TLS for pod-to-pod communication. This makes them both critical and challenging for post-migration. Step 1. It is the NY proxy integration. Integrate PQ-enabled crypto libraries into NY sidecars for quantum safe MTLS connections. Then the certificate management update service for certificate authorities to issue hybrid certificates supporting both algorithms. Then the backward compatibility. Ensure hybrid mode allows seamless communication between upgraded and legacy workloads during transmission. Then the performance monitoring. Track latency and throughput. In fact, as PQ algorithms have different performance characteristics. Securing mesh MTLS is critical because it forms the foundation of pod-to-pod trust in zero trust architecture. Now, the third place to secure it. So it's the secret and ETCD. ETCD stores all Kubernetes cluster state, including sensitive secrets. Protecting data is essential, but post-quantum certificates introduce new challenges. Storage challenge. PQ certificates are significantly larger than RSA ECC, impacting ETCD performance and application. KMS integration. The leverage PQ safe key management service CCAR Vault or AWS PQ KMS pilots for external encryption. Rotation strategy. Implement automated rotation for allowing secrets to minimize exposure windows. Now let's see the key challenges. Post cryptography adoption isn't just a simple algorithm flat. Organizations face significant technical and operational hurdles. So it is 3.2x handshake overhead and 10x the certificate size and 60% library maturity. Now coming to the handshake overhead. So performance penalty compared to the classical algorithms during TLS negotiations. And certificate cycles are really larger certificate, stress ETCD storage and replication bandwidth. And now coming to the library maturity, estimated readiness of production grade PQC implementation across. So now the algorithm, key size and handshake time and compatibility. So the RSA 2048, the key size is 2 KB and handshake time is 1x and the compatibility is universal. And the ECP P256 key size is 55 KB, handshake time 0.8x and the compatibility is universal compatibility. And the Kyber 768, the key size is 4 KB, handshake time 3.2x and it's limited. The challenge extends beyond technical merits. Polyglot microservices environments face inconsistent PQC support across programming language and frameworks. Migration strategy. Successful post-quantum migration requires careful planning and phased implementation. Organization must balance security improvements into operational stability. Phase 1. Implement dual algorithm handshake supporting both classical and post-quantum cryptography for maximum compatibility. Phase 2. Ingress first. Begin with external facing ingress controller where quantum resistance provides immediate value. Phase 3. Service bus. Extend to internal service to service communication through gradual process update. Phase 4. Core infrastructure. Secure etcd and core Kubernetes API communication as the final step. Always maintain rollback options. Candidate deployments and feature flags are essential for managing PQ workload transition safety. This operator approach. Kubernetes operators provide the ideal mechanism for managing post-quantum cryptography at scale. treating security points as code. A custom resource definition. Define PQ policies declaratively using Kubernetes CRD. Ensure PQ saves certificate requirements automatically. Helm chart. Simplify PQ deployment with templated configuration. So here is the sample for your reference. Now let's see the observability. So monitoring cryptography health becomes a core observability requirement in post-quantum environment. Organizations need visibility to algorithm adoption and performance impact. Handshake algorithms in use. So the track with DLS handshake use classical vision, post-quantum as a hybrid the algorithms across the infrastructure. PQ adoption rate. Monitor the percentage of connections successfully post-quantum cryptography to measure the migration process. And the performance metrics. Measure latency increases, error rate, and throughput impacts from larger certificate sizes and computational overhead. You cannot secure what you can't see. Monitoring cryptography health is now a core observability task for SRE teams. So let's see some of the early adopter case studies. Financial services organizations running on EKS and GKE are pioneering post-quantum Kubernetes implementation, providing valuable lessons for broader adoption. High-frequency trading. PQ MTLS implementation in microsecond sensitive trading systems. Performance trade-offs required careful algorithm selection and hardware optimization. Regulatory compliance. Hybrid cryptography helps meet emerging regulatory requirements while maintaining compatibility with existing systems and partners. Let's slice and dice to the stage. So first, test certificate distribution at scale. So large certificate sizes can overwhelm system distribution mechanism in high node count clusters. Second, expect performance trade-off. Budget for 2 to 4x latency increases during handshake and plan capacity accordingly. Then the rollback plans are critical. In case something happens, incompatibility issues can emerge unexpectedly. Always maintain classical fallback options. And now the roadmap and open source. The post-quantum transition is supported by a growing ecosystem of standards, open source projects, and community initiatives. In 2024, NIST PQC started finalized. Early implementation is OpenSSL and major crypto library. By 2027, production-ready PQ implementation, major cloud providers offer PQ-enabled services. And from 2028 to 2030, we are expecting to see widespread adoption, classic algorithm deprecation in favor of quantum-safe alternatives. The key projects are Open Quantum Safe, OQS, CNCF Security SIG, this enhancement proposal. So these are the three key projects. Now, what is the call to action? The post-quantum era is approaching faster than many organizations realize. The time to begin preparation is now, while quantum computers remain in development. So, the inventory dependencies, experiment in staging, adopt hybrid crypto. So, catalog all your cryptographic dependencies in your Kubernetes infrastructure. Identify RSA, usage pattern, and certificate lifecycle. Experiment in staging. Set up test environment in PQ-enabled Ingress controller and service measure. Measure performance impact and compatibility issues. Adopt hybrid crypto. Begin implementing hybrid cryptography for new deployment. This provides quantum resistance while maintaining backward compatibility. So the resources for the NIST post quantum cryptographic standard, Open Quantum Safe project documentation, CN Security Sync PQ working group, Kubernetes PQ enhancement proposal. The future is quantum safe. The cluster you run today may be vulnerable tomorrow. So start small. Experiment with post-quantum cryptography and prepare your infrastructure for the quantum computing revolution. Saying in cybersecurity, being late to adapt isn't just inefficient. It is catastrophic. The post-quantum transition is not a question of if, but begin your quantum resistant journey today. Your future self will thank you for the foresight. Thank you. Thanks for watching my session. Thank you. Thanks a lot.